Welcome back. Our final presenter today is Biosystems Engineer Dr. Nazin Cicek. Biofuels have gotten a lot of press lately, and a lot of money is going towards biofuel research. Around the world, scientists are racing to discover new and better ways to make fuel out of organic waste or to somehow get hydrogen fuel from waste cellulose material. Dr. Cicek, I need to drink some water.
Cicek's.
Okay.
That's
Dr. Cicek is one such researcher internationally known for his research. He began his studies in Istanbul, Turkey, but earned his PhD at the University of Cincinnati. He came to the University of Manitoba in 2001, and today he is the Associate Department Head of Biosystems Engineering. He's received nearly $1.5 million in research funding since he arrived at the U of M and has published over 40 peer-reviewed journal articles. Today he'll share some of his wisdom with us. His presentation is titled Biofuels of Today and Tomorrow. Please welcome Dr. Nazin Cicek.
Thanks, Janine, for a nice presentation and introduction. Okay, so that's me. I'm an associate prof in biosystems engineering. If any of you are interested in biosystems engineering or want to know more about it, I'm one of the people to see. So let's get right into it. What's a biofuel? Let's start there, because there's many definitions towards a biofuel. If you go to the Oxford English Dictionary, a biofuel is generally defined as a fuel that's derived directly from living matter. The question then would be, would plants that have gone through a process of change with pressure and temperature and became coal, or oil, or natural gas, would they count as a biofuel? Because they are directly derived from living matter. So this definition isn't quite what we're looking for. And as everybody else does, I also went to Wikipedia and checked out what they came up with. And you know what? I kind of like this a little bit better. And I want to focus on a couple words associated with biofuels. Here it's defined as any fuel that is derived from biomass. Biomass which is recently living. And it could either be that organism or their metabolic byproducts, what they discharge at the end of the day. And it's generally described as a renewable source of energy. Okay? Renewable source of fuel, which separates it from things like coal, natural gas, petroleum, or even nuclear energy. Okay, so it has to be recently living. What does that mean? Does it have to be living yesterday? Could it have lived a year ago? Where do you separate a renewable fuel from a non-renewable, non-biofuel? It's a bit of a gray zone. Obviously wood, old age forest, could be 60, 70, 80 years old before you harvest it. So that's not really a biofuel. But poplar or willow could come to maturity in 6, 7 years. So maybe that is a biofuel. Okay? So that's an important distinction, and we're going to get into that a little bit later. All right, there's different versions of this stuff. There's solid biofuels. Here's an example of a sawdust power plant in Sweden, where they actually use wood pellets. That's a leftover product from their operations, and they make pellets out of it that they can then use for powering pellet stoves. That is a biofuel. You could also use straw. You can kind of see up there, they're moving these square bales into a boiler system. That plant is in Denmark, where they're using straw, which was on the fields just last year, let's say, a recently living biomass, and power a power plant. Okay? Use it as a fuel. You could use other plant matter. You could use your blue box paper waste. Or you could use food crops. If the food prices are really low, they have used off-grade food crops in Germany, for instance. They take wheat that was kind of not deemed to be appropriate for human or animal consumption, and they put it in a boiler and burn it. That's a biofuel. Now, there is also liquid biofuels. You might have heard about these the most because they have garnered a lot of attention recently. You know, as Janine suggested in the popular press, we've been all over this ethanol craze. That's one of the things. You can make ethanol from wheat. You can make it from corn. You can make it from sugar cane. Or you could make it from things that are not food. And we'll discuss that later as well. But there's other liquid fuels. Oops, let's go back there. such as methanol and butanol, which are alcohols of interest to us because you can use them in a different way, maybe use them for powering airplanes. Here's a picture of an ethanol plant. This is the kind of ethanol plant we have in Manitoba, here in Manitoba. It produces about 130 million liters of ethanol a year and satisfies most of our needs for fuel ethanol. Their feedstock, though, is primarily Manitoba-grown wheat and US-grown corn. Okay, let's move on. What else? So we went through solids, we went through liquids. You could also have biogases. Here you could get that from a landfill. Lots of talk about converting the Brady landfill into a methane-producing bioreactor. Here you're letting the organic waste sort of digest over time, put in some wells and collect the methane, and use that to power a plant, maybe heat up some water, or use it for electricity generation. You could have hydrogen that you can obtain from fermenting things, kind of like what you do for beer, okay? Or wine, or yogurt. You could have syngas. That is basically a thermo and chemical conversion of organic matter. By partially burning it and making gases out of it, you can collect those gases and then use that as a fuel source. That's called synthetic gas. And here's a picture of a gasification process. Sometimes a whole bunch of organic waste, like your garbage, could go in there. And you could partially burn it with a little bit of oxygen, generate these gases, then use those gases. And that would be a renewable way of dealing with that waste. And finally, there are bio-oils. Just at lunchtime, we were talking about some guy that was driving his truck or car with vegetable grease, oil, leftover stuff, and it smells like French fries when he drives around the city probably. That's doable. Some cars can actually use vegetable oil, so you can use straight vegetable oils. You could use waste vegetable oils, which makes a bit more sense because then you're not competing against your, the industries that use vegetable oils for cooking or baking or, what you put on your salad, right? Or you could convert that through a simple method to a compound that's very similar to diesel fuel. Diesel fuel is basically something that you can then use to power your construction equipment, trucks, and heavy machinery. Okay, like in every talk, we have to touch on a bit of history. It's not going to be very boring. Engineers like history only to the extent it serves them. So that's what I'm going to do here. If we look at biofuels and we say, okay, where did these come from? Where do they originate from? It's surprising to see that the fella that invented the 4-stroke cycle internal combustion engine, that's basically, this thing doesn't look much like a car, but that's the starting of your internal combustion engine that we use in our automobiles today. A fella called Nicholas August Otto conceived this to originally run on ethanol. Because when he invented this in the 1800s, there was no gasoline. All right? Now, competitor Rudolf Diesel, as the name suggests, inventor of the diesel engine, which works in a bit of a different way. He invented this and first demonstrated this engine with peanut oil at one of the world fairs in 1900. And powered his engine with peanut oil. So there you go, both of them biofuels. The ethanol that Mr. Otto used came from distillation of potato or grains, ultimately fermenting and distilling that out. So kind of making moonshine. Okay? That's what they refer to nowadays. If you do it in the backyard, not advised. Okay, so some more history. Now, when gasoline came into the picture, things changed a little bit, but even the most popular and widely distributed first high-volume automobile that humankind produced, the Ford Model T, was designed to run both or either gasoline or ethanol, okay? Because originally the ethanol prices were really good. Alcohol was cheap. Now, that changed. You might have heard about something called prohibition, where ethanol production was not allowed because people, besides driving their vehicle, would consume a whole bunch of it. Okay. And that was outlawed at one point, and that really hurt the ethanol industry. Okay? Beyond that, you had the cheap shift to gasoline. Oil was discovered in abundant form. Drilling technology became widely available, and it was just very cheap to bring the oil from the ground and then process it. So ethanol lost out. But it came back briefly during the Second World War, where access to gasoline became an issue. And actually, this picture is from an illustration from the Second World War. German engineers started to blend gasoline and potato-based alcohol and called it, a very German name, Reichskraftspirit. Okay? I think that's how it's pronounced. Basically, it's like, homemade fuel, right? German-made fuel. So they were less reliant on imports. This story is now, similar in the US when people talk about sourcing their own fuel and limiting imported fuel. The Brits did a similar thing. They called it discol. And they basically blended their petrol with grain alcohols to supply them with sufficient amounts during the war. So there's quite a bit of history on biofuels that's not immediately in our present, You can go way back and find these stories. So why would we re-engage in this debate of using biofuels? There's several drivers that are critical. I believe you heard about climate change today already, and the gloom and doom scenarios associated with it. Let's talk about some of the drivers associated with this field. First of all, biofuels are renewable. What does that mean? Every year you can grow this stuff. You're not going to stop putting waste paper into your garbage, right? You're not going to stop eating, so there's going to be waste food. You're not going to stop necessarily using wood products, so there's waste wood, for instance. And every year, you'll be generating new sources of this biofuel. So it's renewable. We're not harvesting stuff that was deposited a million years ago. Secondly, it's carbon neutral. What does that mean? When you burn an organic compound, it releases CO2. But you're just lending that CO2 to the atmosphere. Because next year's crops will pick that up to make more biomass, right? So the carbon cycle presents itself in such a way that we don't emit additional amount of CO2. We're not digging out dino diesel, as they call it, the fossil fuel stuff from a million years ago, which was deposited then, and now release it to the atmosphere. So we are able to pick that up on a yearly basis. Another important advantage, biofuels are biodegradable. When our fuel tanks leak or when we have an accident and we discharge this into the environment, these are easily picked up by microbes, okay, and converted. Whereas synthetic organic chemicals from petroleum-based products are not biodegradable or very difficult to degrade, take a long time. You can grow this at home. What that means is you can make them locally, which has many advantages, particularly if you're an energy importing country. And if you're using waste materials, you're hitting two birds with a stone, right? You're also doing waste management. You're getting rid of waste. Finally, when you burn this stuff, there is less emissions, particularly sulfur and nitrous-based emissions, which would be a significant problem with coal, for instance. Many advantages. All right, let's get to the debate about food versus energy or fuel. You can make biofuels out of food crops. That's what we do right now, as a matter of fact, primarily. The Brazilians have been pioneers in this area. They have lots of sugar cane. Okay? And when the sugar industry suffered from low sugar, worldwide sugar prices, they shifted all their sugar into ethanol production. And during the petroleum crisis that hit in the late 70s, early 80s, when oil just peaked, people were looking for alternative sources of fuel, and Brazil basically took that and ran with it. So they got lots of sugar from sugar cane, but sugar cane is a food crop. You could make it from corn. About 28% of the US corn crop last year went to ethanol. So you can make it from corn. Okay? But you can see the danger there, right? The more of that you divert to fuel, maybe you're going to have less to give away to poor countries, or maybe you're going to have less to feed populations. Oops. And oil seeds, these are things that you use for biodiesel production. They can be canola, they can be soy, they can be palm oil, and all of these are food crops. Now, let's see, can we make this stuff from things other than food sources? Yes, we could go with waste biomass. You could use the corn cobs and stalks that are left over from corn harvests, right? Maybe you can find a process to convert that to biofuels. And that's been done in the US. There's lots of research there because they're significant corn growers. Wheat and rice straw. The straw that's left over from wheat and rice production could be used. You might not know, but rice is the most produced food stock in the world. So there's lots of rice straw around globally. You could make it from sugarcane waste, not from the sugarcane itself, but what's left over. If you have the technology, there's research going on, Department of Energy on that. You could make it from forestry or paper mill discards, things that are left over. Maybe you can make it from municipal solid waste. That's the stuff you ditch into the garbage, right? That'd be nice. Or you could make it from waste vegetable oils. What are those? Stuff left over in your mom and pop, grease joint, right? Or slaughterhouse waste, or that's basically tallow, lard, that kind of stuff. That's fat that you don't use. Maybe you could divert it to a food stock. Okay, gives you an idea. Let's look at what has happened so far a little bit with ethanol. It's an interesting picture of that's billion liters a year on the y-axis there. And you see that Brazil was the dominant producer of it until recently the Americans took over. And you can see there's an upward trend, right? More and more of this ethanol is being made. And there's mandates, meaning there's regulations to use more and more of that blended in with our gasoline. The Europeans have picked that up a little bit. The Chinese produce some of it. And we produce close to 1 billion liters now, with 130 million liters of that in Manitoba. But again, almost exclusively, all of this comes from food crops. Okay? How about biodiesel? The Germans have been leaders in this. They produce lots of rapeseed, which is canola. It's an oil seed. And they convert that right into biofuels. The Europeans have been leaders overall, but the Germans by far are the biggest producers of it. They have a lot of diesel engines, if you've noticed. The VWs and Mercedes and all these German companies have diesel engines, so they use biodiesel. Why not? You can get away with it because they don't have oil wells in their country, right? They have to import that stuff. The US is picking up steam. Canada, not so much yet. Okay, let's get to the food crops to waste biomass debate, dig in a bit further and see which one is more beneficial and why. Okay, just for ethanol as a case study, if you make it from food crops, 50% of your cost or more is actually your feedstock. It's not much money to be made because there's a value for that corn, that sugar cane, that wheat, right? Now, the other thing we have to keep in mind, just like energy, food is a very strategic commodity. Countries look at food as a resource that they need to maintain at certain levels. Inventories have to be there. You don't want to starve your own population in case of an issue. So food is a strategic resource, just like energy. So you have to balance that. The energy balance, that means how much energy do you have to put into growing this stuff, processing it, making the ethanol, let's say, versus how much energy does the ethanol actually donate to your car. When you do that analysis, you find, yes, there's a positive balance, but it's not great. 25% more energy out than in, worst case scenario. Some people have said, it's even negative energy balance, but that's not quite the case anymore. GHG, that's greenhouse gas displacement. How much CO2 can we avoid by using this stuff? It's a certain amount. For every ton of feedstock we use, we can avoid some CO2. And the big advantage here is we know how to deal with food crops. We have these grain elevators. We have rail cars moving this stuff around. We have big harvesters, farmers that know how to grow it. High volume infrastructure is there already. That's why it was sort of the path of least resistance to get to this fuel by using food, right? Because we kind of know what to do. I mean, you're already brewing it for all kinds of purposes. Barley is being used for beer making for years, right? What about waste then? First of all, the good thing about waste is it generally doesn't have a market value yet. You can get it for free. Sometimes you can even get money if you go pick it up. But that's not going to be forever, right? The moment People know you're going to do something with that. It's going to have a price. But for now, it's a negative as far as cost is concerned. That's nice. The energy balance, much more favorable because you don't have to put fertilizer, tractor oil, harvesting, processing is much different. So the growth of it doesn't require much energy. So if you make it from wood or from wheat straw, the energy balance is much more favorable. It's a better CO2 balance. But the problem is this stuff isn't available in large quantities. You got to go pick it up from little places. Maybe you got to go into the forest, pick up the brush. You might have to go to the sawmill, pick up that stuff. You might have to go to the agricultural field to pick up straw, right? So that's a bit of an issue. Now, I guess we'll have questions after, but if I'm really confusing you, just don't worry, raise your hands and I'll try to address them quickly. All right, so this waste is a good idea. We should do that. How much of this stuff do we have? Canada's a big country, right? Lots of waste sources probably. So an organization called BioCap looked at this inventory, Canada-wide, and made a pie chart. And what we find out of that is the Canadian waste resources are primarily in the forestry business. This non-stem woody residue is basically stuff that's left over when we take a tree out of a forest, all the branches and all the brush that we don't take out, right? That's called a waste. Now, we also have wood product residue that's like sawmills and sawdust and so forth, crop residues, that's straw, livestock manure, that's the leftover stuff from livestock, right? Raising livestock. Municipal solid waste, that's what you put into the garbage. Municipal biosolids is what's left over from your wastewater sewage treatment plant. There's some solids that are left over there as well. What does it amount to? When you add that all up, you find that it amounts to about 22% of Canada's total energy needs as far as fossil fuels are concerned. So that seems promising. What about Manitoba? Very different pie chart. Much of our waste is agricultural based, right? That makes sense. Primarily crop residue. We did this analysis, by the way, and we found that about 50% is crop residue, another almost 30% is livestock waste, manure. Got lots of that around here. Now, the good thing is we have so much more energy than we actually provincially use in our waste. We have almost twice as much ethanol capacity from just these waste sources than we consume in the province. Total gasoline consumption in the province is about 1.5 billion liters. So that is interesting and maybe something we need to pursue. So if you were to use conversion systems to convert those waste biomass things into ethanol, by just simply taking ag residue and some of the other more easily dealt with waste, we could get there. We could get to 1.5 billion liters quickly. And even without using manure, which is hard to do, you could satisfy all our gasoline needs. The question is, at what cost? What about hydrogen? The beauty about hydrogen is when you put it together with oxygen, what happens? Water. So when you burn it, the only emission you got is water vapor, right? All these fuel cells cars, the inventor puts like a jug at the exhaust and then drinks that stuff, Look at this, clean stuff, great. Where are you going to get it from? Can you drill a hole and get hydrogen? Lots of it at the sun, but not much here naturally available. So when people talk about hydrogen, let's keep in mind, it is a fuel that burns clean. No carbon dioxide is emitted because H and O make H2O, right? And you can get it by taking H2O and cleaving it out, right, with electricity. But it's not a source of energy. It's not available. It's a carrier, meaning you have to put energy into that, and then maybe you can use it for driving around the car. And anytime you have to go through a bunch of steps, you lose efficiencies. Okay? You multiply those inefficiencies with each other. That's what the engineer is going to teach you right away. And what you find out is, man, making this hydrogen out of electricity, which probably comes from clean sources in Manitoba like wind or electricity, then putting it into a fuel cell and driving around with it is not that great. Why not just use the electricity and drive with it, right? How about if you make from natural gas? We could split natural gas and make hydrogen out of it. Well, then still the CO2 that's off the natural gas is coming off, one. Secondly, natural gas is a fairly clean, nice-to-handle fuel already, right? So there's some issues there. Keep that in mind. Anybody trying to sell you hydrogen, keep that in mind. Now, if you could make it from waste, wait a minute now, that could be interesting. Okay, let microbes make this stuff, almost like burp it out. Or the other stuff, I'm not going to. All right? So that has some potential. Yes, if you can get hydrogen cheaply without sacrificing a good fuel in the process, do it. Because when you burn it, no emissions. You remember this guy, right? He was a big hydrogen fan. And hydrogen economy, hydrogen highway in California was going to put all these hydrogen pumping stations everywhere, and hydrogen was the future. And that's a hydrogen fuel cell car there, a Toyota. Now he's changed his tune a little bit. He says, man, maybe we should drive electric speed cars, like that Tesla there. So let's just short circuit the hydrogen business and just put big batteries into these vehicles and drive on electricity. You know the challenge with this thing? It goes from 0 to 100 in 5 seconds or less. It's just a beast. But it doesn't make any sound. So the guys that are driving is saying, it doesn't sound good to me. So they put in audio options to make it sound like a Ferrari or a Hummer. That's real. To sell these guys. Now that costs you about $80,000, so maybe it's not the option for everybody. But this takes the electric car from this sort of ugly duckling thing into something that's much more appealing, even to Mr. Schwarzenegger. All right. So then, if I were to make this from hydrogen, make hydrogen from waste, what could I do? I could actually recruit microbes and put them into a fermentation environment. That's basically a conversion system, kind of like your brewery tank. Whoa. Is that me? If I take sugar and give it to these bugs, they can make quite a bit of hydrogen out of that. Don't worry about what I said there as much. It's basically the best case scenario is if you make acetic acid as a byproduct, that's some of what they pee out. You can also get a lot of hydrogen. But you know what? These bugs don't do what we tell them to do. Most of the time, they produce a whole bunch of other stuff. And just like you and I, when our metabolism changes, we make different waste products, don't we? Same thing with these guys. All right? So if you want to make hydrogen from waste, you've got to choose the right bug and maybe use that bug. I'm saying bug, it's a microorganism. You can't see it. It's not crawling around. And use that microorganism, maybe manipulate it, force it to make only the things you want it to make and not the things you don't want it to make. The problem also is when you make hydrogen, bugs don't like it. It's an end product inhibitor. The more you make it, the less desirable it becomes for the microbes to make more of it. So one thing we could do is maybe jack up the temperature because gases don't like to be in solution when you up the temperature. And if you can find microbes that operate at very high temperatures, we could make the gas and just let it, leave the system. And suddenly you have microbes that are much happier to make more of this stuff for you. Okay? I'm getting into this a little bit because I'm going to tell you right away what kind of research programs we have at the university, my labs, and so forth. And this sets you up a little bit to understanding some of that. The problem is converting waste biomass, which is primarily cellulose. What's cellulose? It's a bunch of sugars stuck together that the plant fixes to make more plant mass. It's the most abundant fiber biopolymer on this planet. Plants make a whole bunch of it every year. It's basically, the muscle and meat of a plant is cellulose. Okay? So taking cellulose, which is designed to be a building product for the plant, and cleaving that up and making hydrogen is hard. Some microbes do a decent job, but there's no commercial application that does this quite yet in an effective way. We can get the hydrogen. I'm making it in the lab right now. but, you know, it can't compete with the other fuels out there. Okay. So what kind of waste would I be interested in using? I could use forestry waste, because forestry waste is 40% cellulose, which my bugs like, 30% hemicellulose, which is another component of wood, which some bugs also like, and you know, the rest is lignin, which no bug really likes. All right? So we're going to have an issue there. But guess what? That lignin that's in that wood is a great adhesive used for resin production. So if you would find a way to get that out of there, you know, and use it for that industry, maybe there's a benefit there, right? Same thing with crop residues. You can get 40-20 distribution. Manure even has quite a bit of cellulose. And your paper waste, the stuff that you're going to be putting into your blue box as paper, has quite a bit of cellulose in it. So going back to the pie chart of Manitoba, we got all of these stuff, right? All of these things are available to us. The question is, who's going to do the work to find the right means of converting that to a fuel that's clean and sustainable? Well, we're trying. What we're trying to do, instead of using a bunch of microbes in sequence, we're trying to find the ultimate cellulose eater. Okay? Go survey the planet for cellulose degrading microbes, and then find out what would they produce if they eat some of this stuff. And then put them into a reactor, which is my expertise, basically put them into a home, a vessel, and optimize the conditions where these guys are super happy, okay, and make the stuff you want them to make. That might involve acidity, temperature, mixing, nutrients, how much food they see a day. You know, you don't want to overfeed them because they get acid reflux just like you and I, and all kinds of stuff. Now, you can find the right bug, you can feed them the right things, or what you could do, you could just harvest the enzymes from those bugs, which are the catalyst to actually this conversion process. You know what a catalyst is a substance that makes this conversion happen without being used up in the process. And maybe instead of using the microbe, we can use these catalysts, these enzymes, because the microbes are finicky. Okay? They're living things. They die on you. You know? The student forgets to feed them one day, and then you got to start from scratch. But the enzymes are not. They're like chemical substances. So maybe there's a benefit to doing that. All right. How am I doing here? Okay. Let's talk about what we do around here. I'm going to give you some examples. I hope I can fit them all into the time I have. We have a program that has as a partner Husky Energy. Those are the guys that make petroleum, yes, but they're interested in making more ethanol. Whoa. And we have a bunch of people working on different things. We have plant scientists trying to find crops that have higher starch yields, meaning where you can make more ethanol out of it. You have other plant scientists that look at exactly what kind of starches we could make and how those starches could be used by microbes, by yeast. We have animal scientists that use the leftover product from ethanol production and try to feed that to humans or animals, so we have a byproduct that is valuable and drive the market. And we have biosystems engineers, myself and a couple others, that are looking at optimizing hydrogen production, reactor design, other things like that. So that's been ongoing for a few years. We have published some work on that, and we've made some interesting progress. We've used this bug a lot. It's basically a microbe that's anaerobic. It's called Clostridium thermocellum, complicated name. Anaerobic meaning it doesn't like oxygen. It was discovered in a compost pile at one point. Okay? And the good thing about these guys is, see, that's the microbe itself, and on its surface it has these little bumps. That's how it holds on to the cellulose. It actually lives on its own food. Okay? And is very prolific, very, has high rates of degradation, let's say, of the cellulose to the end products. It's just a great cellulose eater. The thing is, what we like about this bug primarily is it really likes high temperatures. You know, when you put your hand into a compost heap, I suggest you don't do that. because it's going to be about 60 degrees C. Okay? It's going to burn your hand in the middle of it. And that's where we got these bugs from. Because they like anaerobic conditions, no air, and they like high temperatures. And remember, I said high temperatures are good because we can get more hydrogen out of it. And if this is your cellulose and this is your bacterium, those little bumps are actually, we discovered that it's a complex way of attaching yourself to the food and then consuming little by little this cellulose through these channels and bringing them into the bug. It's kind of like a bottleneck that we can control, how much food they should consume. It's a nice thing because we can then engineer the microbe a bit better. And the other thing we like is that it produces ethanol and hydrogen, along with some acids and CO2. So it was a nice target organism. We've been working it for about 4 years, maybe 5th year now. The other thing that was interesting is some researchers have now fully sequenced its genome. What that means is we know exactly what genes are in that bug. We know how they're organized. And now we can start playing with its genome, maybe limiting the production of some of these things and favoring others. So we have a genetic engineer working on that and a metabolic engineer to change its metabolism. Okay, some cool stuff going on there. So as I said, we have genetic engineers, reactor engineers, microbiologists working with this stuff. And we have used these reactors. You kind of can tell a little bit here. It's a fermentation system. It's small. It's about 10 liters. And we've used all kinds of waste materials in converting this stuff into hydrogen and ethanol. This stuff is pure cellulose. You can get in a laboratory environment. You're not going to get much of that. That's shredded white paper. This stuff is an agricultural waste source. Okay? Actually, no, that might be a wood fiber, actually. Looks like an ag waste, so same thing. It's fiber from a wood processing facility. And what we try to do is, make these environments such that this conversion would take place, and then start tinkering with the parameters. Another project, we use actually the leftovers from ethanol production called distiller grains to make biopolymers. These are things that are used as building products for polymers, plastics. Like much of petroleum now is not much. A good chunk of petroleum that you get from the ground is used to make plastics, not to burn. If we could have our microbes make that, that'd be interesting too, right? We'd further reduce our dependency on petroleum and fossil fuels. So we've looked at this concept a little bit, and our feedstock in this case was these byproducts from ethanol production. And we made some interesting gains there, and I'm not going to go into the details necessarily, but the purpose, ultimate goal is to make more of these building blocks to make polymers. All right, that's on the hydrogen side. I figured I'll give you a couple other examples so you don't just think we're working with bugs that make hydrogen ethanol. I have a project that deals with using biomass that you might have seen in the ditches of Winnipeg or in the wetlands, in the Delta Marsh area, in the Winnipeg Marsh area, in Netley-Libo Marsh. This is biomass that grows on a yearly basis. Basically, cattails are just prolific species that grow a whole bunch of cellulose on a yearly basis, okay? Every year, they can get up to 12 feet tall. In the process, they'll suck up nutrients because just like every organism in this room, they will need nutrients. And the goal of this project was to remove nutrients from water that would go into Lake Winnipeg. And you know what the problem with that is, right? Phosphorus in Lake Winnipeg causes algal blooms, all this algae, this sludge on your beaches. Nobody wants to swim anymore. Property prices might plummet. I don't know what's going to happen. People panic about it. Let's remove phosphorus. How are you going to do it? The river is bringing it in. Maybe a way to do that is attack the problem at the marsh level, where the river ends up in the lake, right? The delta area. One way to do that is remove these nutrient-absorbing species of cattail, then convert that, because it's cellulose, right, into a fuel, and then use the ash that's phosphorus-rich and put it back onto land. as a nutrient. Why put it in the lake where it's causing headaches, right? Let's use it for agriculture. Does that make sense? Kind of makes sense. No, it's easier said than done. So we had to look at a whole bunch of things here. And we had people like Manitoba Conservation, those are the environmental guys. We had Ducks Unlimited, who worry a lot about waterfowl and, you know, if you harvest this biomass, what will happen to the ducks, right? When should we harvest it? You can't go in there when there is an ecological diverse area. So we decided to go in there when it's covered in ice, February. Work with the International Institute of Sustainable Development and some other people to ultimately get to a point where we can see this as a fuel source and also remove a compound like phosphorus that we don't want in our water. So where is this marsh that we're working at? That's Lake Winnipeg over there. That's the Red River feeding it. And right there's the Netley-Libo Marsh. It's 250 hectare, big area. You kind of can see that photo in the back. And you know what? Much of the phosphorus that goes into Lake Winnipeg that causes all these headaches comes from the Red River. And we had set up some sampling sites out there. Our students have been working there for the last 4 years. This is a graduate, now an undergrad student, but is now a graduate student that looked at what will happen to the phosphorus in this marsh when we harvest these plants. Will it actually be sucked up from the soil, or will it be removing it from the water? It's an important question. Right? We had this fella here, he's a PhD student, Richard, go out there, harvest this stuff to do sampling. He's very happy harvesting it also in August just to see what the difference would be. And we collect this stuff. You see how tall those plants get, eh? Right there. Michelle here is sitting on the pile that she harvested, proudly, standing actually. And then we had to take this stuff and put it into an energy conversion system. We used a gasifier in this case. We had to measure emissions. Where do these compounds go? Do they end up in the ash, or do they get released back into the atmosphere, which means then they get deposited in the lake, and the whole thing is useless, right? So we had to really study this to a large extent. Whoa. Okay, that wraps this one up. So there's a snapshot where we do ecological engineering and still worry about biofuels, because the cattail is a biofuel. Every year it grows. As a matter of fact, when we harvest it, every year it grew thicker, which is kind of neat, because we kind of cleared up the area, right? You can see that. Okay, another thing, anaerobic digestion. What the heck is this? You know what? Every one of you are doing that right now. You are doing anaerobic digestion if you had a cookie at the break, or if you had lunch, for that matter. It's the conversion of organic matter to gases when it's left in an anaerobic environment. Your colon does that. Okay? You can use this process. You can engineer this process and convert livestock manure, in this case here, which is, remember, a big source in Manitoba. Put in a digester, make gas, methane gas, which is combustible. That's kind of similar to what's in your natural gas pipe. What you put is similar to propane, you know, what you use in making, you know, a steak on your barbecue. And tackle a few issues at the same time. Beyond making gas, which could be used for heat and power, you could also remove the odor from the manure. Everybody's familiar with that, right? If you drive around rural areas or get into my lab. Pathogen reduction, that means you can kill some of the bugs that live in there that you don't want to put on the land. And you can even improve the fertilizer value of this manure for farmers. Just a depiction of what anaerobic digestion is. You take all these complex materials that you eat, you break into simpler materials. There's a whole bunch of microbes that do this. Then they break them into acids. Then they break them into hydrogen, carbon dioxide, and acetic acid. And ultimately, the next step is to make methane. So it's a multicultural environment. Many bugs living together to ultimately make methane. Okay, that's what's going on in your colon. Many, many different bugs. And that's what you have to cultivate in these vessels to get this thing going. You can put them into big lagoons, which are ponds. You can put them into tubes, kind of like your colon, where you slowly pass this thing through, called plug flow reactors. You can put them in a vessel and mix them up. And there's many ways you can do this. You can either do this on farm individually, or you can have one big processing facility where all the farmers bring in their manure. That's been done in Europe. Good example of that is Germany, very progressive in this biogas business. Here's some examples of these plants. They have built already almost 2,000 of these small plants, farm-based plants, centralized plants. They have done these primarily because electricity and power is expensive in Europe. Government provides them with grants to build these things and purchases that green power at a premium. All those conditions don't exist here. Also, there's a carbon credit. What that means is that's going to come here. You know, when you have the greenhouse gas cap and trade system, whatever we're going to get, we're going to value carbon in a certain way. And it's going to cost you money to put it in the atmosphere. So in Europe, that's already there, so that makes this a favorable technology. All right? How about Manitoba? Can we do it here? All right. The problem, well, first of all, let's look at the livestock industry in Manitoba. Pigs outnumber us 3-1 at any given time in this province. 3 million pigs to about 1 million people. We actually produce about 9 million pigs in this province a year. Every hog makes a ton of manure annually. You don't make that much. You're just peanuts compared to these guys. They really can make this stuff. All right? 21% of all the hogs produced in the country are made right here. Now, people might say, oh, that's disgusting and whatever. But, you know, they still like their pork chops, don't they? So, somebody's got to make this stuff. And it needs to be a sustainable industry, no doubt. But let's not just say that's no good for us, let's not have it. So we're going to keep having this stuff that produces about $1 billion worth of economic stimulus into this province, the favorite word nowadays. And it produced a lot of jobs. Farmers are happy making this stuff, you know. So we have to deal with it. What do they do with the manure? Generally, they just spread it onto cropland. And that's a good thing, because organic fertilizer is the best way you can raise crops, right? Don't let anybody else tell you that the white pellets you put on a farmland is any good, because you got to make that somewhere. Okay, it's got to come from a mine, phosphate mine somewhere in China, or you got to make ammonia from maybe from natural gas. Okay, so organic waste is not a bad thing if you do it sustainably. But beyond the nutrient value of this stuff, you could use the gas then to also power the farm, maybe heat up certain things, maybe make electricity like the Germans do. What's the problem with that in Manitoba? Guess what? It's cold here. And you know your gut is at 37 degrees C, right? Those bugs don't like to be in the cold. They like to be about 35, sometimes up to 50 degrees C. That poses a problem. Other problem is electricity is very cheap here, right? We make it from hydro and so forth. So making electricity out of biogas is maybe not the smart thing for a farmer to invest in. It just doesn't get a value, right, back. And beyond that, we don't really have any value put to greenhouse gases yet, or nutrients that we don't put in the lake and so forth. So there is no drivers to make this thing go. So we said, okay, let's do some research here in Manitoba. How can we improve this thing? Remember, if it's really cold outside, most of the gas you actually make has to go to heating up the environment where you house these bugs, right? So let's look at insulation. Let's look at putting these environments into passive heating zones, use solar energy. Let's look at adding ingredients into this manure that makes way more gas than just the manure itself. So maybe we can make more gas, so the amount we have to sacrifice in the winter isn't going to hurt us that much. You with me? So that's what we do research on here. This is just completed this work, where we actually put something called glycerol, which incidentally is a waste product of biodiesel production. And we don't know what to do with it. But it's a high calorific value. It's like the fast food for these bugs. They love it. It's like McDonald's, right? So they digest that quickly. And you can put a whole bunch of it into manure, and suddenly you produce 2, 3, 4 times as much gas. Now, that has to be optimized. You can't give them too much because they don't like it, and so forth and so on. So we studied that. We tried to find the optimal glycerol addition rate to manure to make this thing work. We used these little digesters. We collected the gas. We measured how much methane is produced. That's the glycerol left over from biodiesel production. That's black stuff. That's what we added. All right? Could be toxic, so we had to see how these bugs reacted to that stuff. So that was a study conducted. We found some really interesting results. Another thing, we said, how about we put these digesters into a passive solar heating environment? What does that mean? That means instead of being at minus 25 outside, if you walk into a solar greenhouse, that's basically an area where you have a solar wall that heats up the space at nighttime. You can bring up the ambient temperature around these vessels that we put inside that greenhouse. These guys, those are your digesters. We almost completed this facility. It's going to come into operation this summer. Suddenly, you know, northern Manitoba might become southern Ontario or Missouri. See what I'm saying? Or Germany. So you got to play with this energy balance, not just from making more gas, but keeping more of the heat inside. Couple more items and I'm done. One project we're pursuing is we talked to New Flyer. You know those guys? They make the buses that everybody rides on. They are huge into making alternative fuel buses. They made the first hydrogen bus. They produce 50% of North America's buses overall, and they sell the most hybrid buses. So we said, why can't we make a bus that uses more Manitoba hydro green electricity, and all the rest of the fuel should be biodiesel? Okay, let's work on a demonstration. Manitoba Hydro was really pumped about that because they said, okay, if you have these plug-in hybrid vehicles, these plug-in hybrid buses, we could power them with Manitoba hydroelectricity. Electricity that would be wasted, let's say, at nighttime or sold at a very low price because nighttime you don't need much of this stuff, okay? And the Manitoba biodiesel industry was interested because obviously it's a market for their biodiesel. So we're working on getting this demonstrated. Biodiesel, when you burn it, produces less emissions. Here, all these are emission improvements. And you could make it from canola or hopefully eventually from waste vegetable oils, from tallow, from slaughterhouse waste, and so forth. So working on this one. Final slide, I think. So, what did we learn today? Now, this is not really the future of biofuels as what's going to happen in 25 years. I really don't know what's going to happen in 25 years. Because 25 years ago, we didn't really think about biofuels, right? But what I do know from the last 6, 7, 8 years of experience with this stuff is that we can't ignore biofuels. As much as we would like to go away entirely from fuels and just drive on electrons, meaning use electricity, our lifestyle isn't going to allow that for a long time, right? So we need fuels. Let's keep biofuels as one of the options, and let's make them sustainable, right? Let's do more work on waste biomaterials than on food. So I'm, basically blowing my own horn here because that's what I do. But I think that's the only way we can get to a point where we're going to be sustainable. Certainly the future is going to involve things like cellulosic alcohol, cellulosic hydrogen, waste oil biodiesel, waste material biogas production. It's going to be there. It's not going away. And it's not going to be easy because we consume 86 million barrels of oil a day. It's a lot of oil. Okay? And there's economic hurdles. When the oil prices are like today, or it's $40 a barrel, nothing looks good. When it's $140 a barrel like last summer, all these technologies look great, okay, because they're competing against that. Finally, I want to encourage you to come and look at us as an opportunity for moving forward with your career. If you want to do biofuels research, if you want to be involved in biofuels, bioenergy, biomass, place to come is biosystems engineering and engineering generally. And there's more jobs than there's people in this area right now. So make a lot of money. All right, thank you.
Thanks. Did anyone have questions for Nazin?
I just had a question about the sustainability issue. If we're using crop waste, and I guess especially forestry waste, is that not robbing the sites of biomass that's used to regrow and keep this situation sustainable to begin with? I know from a forestry perspective, is one of the major initiatives in the last few years has been to leave as much biomass
Yes.
I'm just wondering what your thoughts on how that would affect this site long-term in terms of keeping it sustainable.
Very good question. Any study that looks at taking straw off of agricultural land or waste biomass off of forestry land would have to include the amount of material that needs to stay there, no doubt. And that could be upwards of 80%. But let's remember, we have an artificial situation. When you do forestry, you're growing trees to harvest them and leaving all the branches, leaves, and even somewhat medium to large-scale trunks behind. That doesn't help your soil. It actually robs your soil. If you look at clear-cut areas, those branches do not result in the growth of new forests as much as if you clear those areas. I'm not talking about going into an old-growth forest and taking stuff from the soil. That is definitely not sustainable. But if you're doing clear-cutting, if you're doing forestry as an industry, and going in there anyway to grab the stem and kill the tree, let's make sure we think about how we're going to deal with the waste. As far as agricultural straw, for instance, is concerned, or corn cobs, corn stalk, some of it needs to stay on the soil to prevent erosion, to provide nutrients, to provide water retention, but not all. It's a very good question. You can't take everything.
Any other questions?
Just a comment on this one here. You hear these gloom and doom things about the environment and about global warming, obviously. If you've seen The 11th Hour, for instance, great movie, I suggest you see it. The first hour is all about the problems of the world, erosion, other things. The half hour that's at the end is about solutions. And in my opinion, you, and I include myself, I'm not that old, are the generation that gets to imagine everything from scratch, gets to do stuff that's never been done before. To me, it's not a depressing time. It's a beginning, not the end. The question is, are you willing to think, right? And to think over everything, how you heat your homes, how you drive your cars, what foods you eat, entire societal structures. Okay? So to me, this is a really, really exciting time to be in the environmental and fuels energy area. So don't let anybody discourage you from that by, painting a very dark picture. Sorry, go ahead.
Okay. Thank you, Dr. Cicek.
My pleasure.